Hello, this is Jack Jackson. We're going to continue our series of videos on continuous probability distributions. In this one, we're going to introduce the most important kind of distribution that there is, and that's the family of normal distributions. So, why are these important? Well, for a couple of reasons. One is that it does model many real-world data sets. So, if you did a large population and we looked at like heights of people or weights or intelligence, lifespan, other biometric measurements, blood pressure, they would have a tendency to follow a normal distribution or something at least closely approximated by that. Measures of manufactured items, mass, weight, volume of liquid dispensed by a machine, length of something that we're making. Those things have a tendency to follow normal distributions. Exam scores on large-scale exams like the ACT test or SAT test, and several other many examples have real-world data that can be closely modeled by a normal distribution. So it's very useful in that sense. But probably the most important reason is because of something called the central limit theorem, which we will get to toward the end of this unit, and it tells us in the risk of giving away the punchline here coming later, is that the distribution of sample means approaches a normal distribution as the sample size increases. And this actually is the thing that actually gives us the setup to move right into inferential statistics in the last unit. So that's going to be an important theorem for us, and it has something to do with normal distributions. We'll get back to that later, but let's take a look now at some normal distributions and see what they look like. So here is the PDF graph, the probability density function graph, for a standard normal distribution. Now, standard normal distribution means it has a mean of 0 and a standard deviation 1. And actually, like all normal distributions, the graph is mound-shaped. The PDF graph is mound-shaped or a bell-shaped curve, and it's symmetric about the mean, which in this case is the y-axis, x equals 0. And so since it's perfectly symmetric, it has a skewness of 0. The probability that x is less than the mean is the same as the probability that x is greater than the mean. In this case, probability x less than 0, probability x greater than 0, so that's a probability of 1/2. You can see the symmetry, a mirror image around the y-axis. The part on the right side in the first quadrant is a mirror image of what's on the left side here in the second quadrant on this sample. So it turns out the mean, median, and mode are all the same. Anytime we have a symmetric distribution, the mean and the median are going to be the same. Okay, and so you can think of the mean, remember, is like the balance point. So if you had like a solid here, and we put a balance right there at the origin, this thing would balance. That makes it the mean. The probability to the left and right of this are both 1/2, and that makes it the median. The mode is also the same point because it's the highest point on the graph. In this particular one, if it's a standard normal, it has standard deviation of 1. Other normals have different mean and different standard deviation. But here's the formula for the PDF of a standard normal distribution. It's 1 over the square root of 2 pi times e to the power negative x squared over 2. Not a real complicated formula, but it does involve several things. It involves e, it involves a 2, we got square root, we got pi in there. Pretty interesting that it turns out that both of these special numbers, e and pi, those special irrational numbers, actually show up in this formula. So it's kind of interesting. So let's look at some other characteristics of the graph. Like most PDFs, it's 0 on the outside. Well, it's not really 0. It's actually positive everywhere, but it's approaching 0 on the right and left side. So those has a horizontal asymptote of y equals 0, or in other words, the x-axis on the extreme left and extreme right. It's going here, coming in from the left. It's concave up, like a right side up bowl, increasing, and it reaches an inflection point right here at -1, where it changes concavity to concave down. So it's like an upside down bowl, but still increasing. It reaches a maximum at the mode here of 0. 0 is the mode. The maximum value is a little shy of 0.4. And then it turns around and comes back down. So it's still concave down, but decreasing. Reaches another inflection point right here at exactly 1. and it turns around and goes back up. So in general, a general normal distribution will have a mode, median equals mode, which will be the highest point here in the center. So no matter either of those three measures of the center are the same thing. And the inflection points will be at the mean plus 1 standard deviation and the mean minus 1 standard deviation. So let's work with this a little bit. Get your calculator out, and let's put this formula in for the PDF in Y1 in your calculator. If you need to, press pause to get that in, and then hit play to keep going after you've done that. Okay, so we're going to assume you have that in your calculator. Okay, and we're going to calculate some of these areas. Let's see, I'm going to go ahead and make sure this is in my calculator as well. So, okay, so this is basically it, but this is the more general version. So that should be a 1 there for the standard deviation. And the mean is 0, which is right there. So this is sort of the more general version that I've got right here. And the standard deviation is 1. So I'm kind of thinking ahead a little bit here. So that's equivalent to the same formula. Okay, so I've got it in the calculator. Now, the first thing is, how do we know that this is a legitimate PDF graph? Well, certainly if we graph it, or even without graphing it, we can know that e to any power is positive times this positive coefficient is a positive number. So first condition is the y's have to be positive or 0 everywhere, which they are. And it turns out that you know that that means the graph is always above or on, in this case above, the x-axis. Now the other thing is the area under that curve has to be 1. It turns out to show that analytically is a little bit challenging. It's actually a project I give my Calculus 3 students. That's a little bit of a challenging project, certainly too challenging for us in this class. But it is something we can convince ourselves is true numerically using our calculators. So let's go ahead and graph this. I'm going to graph it from -7 to 7 on the x-axis, and just make the x scale 1. And I'm going to go from -0.1 to 0.4 on the y's. And let's take a look at the graph. Hopefully we're going to see this bell-shaped curve when we do that. Okay, so what's the probability it's within 1 standard deviation? Well, we can shade that. Remember, we can shade the region between -1 and 1 by using the calc integral. So second trace, calc, and choose number 7. We've done this before. Lower limit of -1, upper limit of 1, and it will shade in that value and give us that area of about 0.6826 whatever. So about 68%. From the home screen, we can do that as Math 9 and go from -1 to 1. And I have the formula in y1, so let me just go ahead and get that out as y1 dx. And again, that's the same number. So that is from there to there. Okay, so here it is shaded. Here's some of the screens that we just saw. Here's the formula, new operating system, old operating system. There's the graph. I picked a window, very similar looking window. Here's the integral at the home screen. Here's the old school version of that right here. And there's the shading there. So it's about 68%. So we can put that in our table. What if we go out a little further? What if we go 2 standard deviations out, from -2 to 2? Okay, well, going from -2 to 2, I can just do I can say give me my same thing back again, but change this to 2 on the top and -2 on the bottom, and it's going to be bigger than 68%. It's going to be a little bit more, and we get that. Now, normally we would want to take our drawing and clear it out. So there it's about 95% is what we're looking for. If we want to shade it, then we want to go to calc number 7, the integral, And so it's going to draw it again for us here. And nothing's shaded. And we're going to get it something shaded by plugging a lower limit of -2 and an upper limit of 2. And it's going to shade it and find an area there. So that's the probability that is between -2 and 2. Either from the home screen, old operating system looks like this, newer one like this. There it is from the shading screen, from the graphing screen. And anyway, we see it's about 95% of the probability is there. So we've gone from 1 standard deviation. Most of the data is pretty close to the mean, only 1 standard deviation to the either side, and that's 68%. Go 2 standard deviations either way, that's 95%. And by the way, I'm saying this not just saying from -2 to 2, but actually 2 standard deviations below the mean to 2 standard deviations above the mean, because yes, this does generalize to any distribution that is a normal distribution. Okay, so I'm not going to push all the buttons on the calculator, but here it is for -3 to 3. There's the screenshot. There it is there. You can try that on your calculator. Notice we picked up more area now. Nearly all of it, actually. Over 99.7% is within 3 standard deviations. Here it is for -4 to 4. Within 4 standard deviations, 99.994% approximately. And here's for 5 standard deviations. Wow, we're getting really, really close to 100%. Close to 1 for that area. 0.9999994, etc. Very close. Here it is for 6, -6 to 6. 0.999999998. And when it gets from -7 to 7, the calculator just gives up and says, hey, I can't tell it apart from 1. So we've reached the limits of the calculator when we're just going from -7 to 7. Certainly from -10 to 10 is certainly going to get it. So when you're looking at this, it's not to say that there's not this isn't truly 1, it's 0.99, a whole bunch of 9s and something else. But those 9s are enough that when you round it off to the number of digits that the calculator holds, it turns out to be 1. So I think hopefully by now, looking at these numbers here, we're pretty convinced that this area actually really is 1 as is required. Also, this leads us to something that actually turns out to be true about all normal distributions, no matter what the mean is and what the standard deviation is. They all have this basic same bell shape. They all have the 2 inflection points here. The inflection points always occur at mean plus 1 standard deviation and mean minus 1 standard deviation. And we get this basic shape. The mean, median, and mode are all the same, whatever it is. This might not be 0, it might be something else. The standard deviation might not be 0, might not be 1, it might be something else. But you still get this same basic shape. And if you play around with the scale of your graph, then they're going to look pretty much the same. So there's the mean. If we go to the mean to mean plus sigma, that's 34%. Mean to mean minus sigma, this area right here is 34%. So a total of about 68%. That's rounded off, of course. But about 68%. Here's a few more decimals there in this TI-84 picture there. If we go from the mean plus 1 sigma to the mean plus 2 sigma, that's 13.6% there, and it's likewise a mirror image over here. So when we go from there, from mean minus 2 sigma to mean plus 2 sigma, that's a total of 95% there. That's an area that looks like this one here in the middle of the 3 TI-84 screens. And this one here going from -3 standard deviations below the mean to 3 standard deviations above the mean. That's from mu minus 3 sigma to mu plus 3 sigma. We're picking up an extra 2.1% on each side right here, these little pieces, for a total area of about 99.7%. Sometimes this is called the empirical rule, and the empirical rule really just only applies to normal distributions. And the normal distribution is 68% of the data falls within 1 standard deviation of the mean, 95% of the data falls within 2 standard deviations of the mean, and 99.7% of the data falls within 3 standard deviations of the mean. And of course, the closer the distribution is to normal, the closer these percentages are going to be. So a lot of data that's mound-shaped and symmetric then is going to be maybe not exactly these percentages if it's not exactly normal, but at least somewhat in this ballpark. So those are some basic characteristics of what the graph's going to look like. Now let's start with the normal, standard normal, and notice the only difference in this formula and what we had earlier is now I've replaced x by x minus mu. How is that going to affect the graph? Well, try that on yours and try it by putting in different values for mu. Try putting in, say, -3, -2, -1, 0, 1, 2, and 3, and see what all those graphs have in common and what's different about them. Try it on your own and then come back when you're done. Press pause now. Okay, well, here's the graphs in Graphmatica, and you can see the different color graphs. The one in the red in the middle is the one we had before, the standard normal, which has a mean of 1. All of these have the standard deviation of 1, so the only thing is I've changed the mean. Now notice in general, you may remember from your algebra classes that if you have a formula with x's and y's and you replace x by x minus h, then it's going to shift h units horizontally. So if I replace this by x minus whatever the mean is, it's going to shift by the amount of whatever the mean is. So the new mean is going to be there. So that mu is appropriately labeled. It is, sure enough, the mean. So if you put a 1 where the mu is, you're going to get this graph here, and you're going to see it's centered up at 1. If you put a 2 where the mu is, you're going to get this graph right here, and we can see it's centered up at 2, and so forth. Okay? How can we verify that this really is the mean? Well, one way we could do it is this way. If I have this situation here, right here, I've still got a standard deviation of 1, and if I integrate x times the PDF, I should get the mean, mu. Is it the same as this mu here? Well, we should be convinced graphically by looking at this because of the symmetry, but we can also convince ourselves numerically with our calculator by doing this. So we've got this thing here. I've got m where mu is, and if I put 2 in mu and I integrate this, now technically it should go from negative infinity to positive infinity, but if you go mean minus 10 standard deviations below and above, that turns out to be just as good. And we integrate x times the PDF function, we do get the same value that we put in for m. If I put in a different value for m and do that same integral, I get that same value out. So no matter what value I put in for m, you can try it with your own, whatever value you want, and you'll see you're going to get the output, the same value you have for your m. So in fact, that does give us some further corroboration, some numerical evidence that surely is the mean. Okay, what if you have, similarly, let's verify that the sigma in the formula is in fact the standard deviation. Okay, so this actually is the general form for the formula of a normal distribution. F of x equals 1 over sigma times the square root of 2 pi times e to the negative x minus mu square over 2 sigma square. So notice when sigma square is 1, you can basically erase that, and when mu is 0, you can erase that, and that gave us our standard normal distribution. So how can we convince ourselves that the sigma in that formula truly is what it's supposed to indicate, the true standard deviation? Well, one way we can do it is to convince ourselves numerically using the calculator. So remember, in general, the variance is the expected value of x minus mu square, which is the integral over all x's, that's negative infinity to infinity, of x minus mu square, times the PDF formula, there it is, dx. And what this should turn out to be is the sigma square, the same one that we have right here. So it's going to be the square of whatever that is there. So here's what I did, is I put in the formula, where the mu is, I put m, and where the sigma is, I put an s. Okay? In this formula, the PDF formula. Okay, so now I have the general one in. I can store anything as m and s. In this case, I happen to store I think I stored 4 in M, but it doesn't matter. Store anything you want in M. And then I stored whatever I wanted in S. So here I stored 5 in S. And I'm going to integrate, instead I can't put negative infinity infinity, so I'm going to do M minus 10S to M plus 10S. And then I'm integrating x minus M is mu, x minus M squared times y1. Y1 is my PDF formula. And that the rest of that just says dx. Integrated, I get 25, which is the square of the S. So that checked out. Change it to a different S. 4, store S, run it again. Now we get the square of that S. We get the 4 square is 16. That checks out. So you could do this with different values of M, different values of S, and every time you do this integral, you're going to get the square of whatever S is. And that verifies that that sigma is in fact the sigma that we want. Okay? Well, what happens to the graph of the general normal distribution if we leave mu fixed but change the value of sigma? So again, there's our general form. What happens if we just leave mu fixed? Let's say we leave mu fixed at 0, for example, and put in some different values of sigma. Now remember, sigma has to be standard deviation. It has to be a positive number. So let's try these numbers. Try sigma as a half, 1, 2, 3, 4, 5. Maybe try those. So get those 6 graphs and see how they compare. Try it yourself and then come back when you're done. Well, here are the graphs all graphed together with different colors using the Graphmatica program. Now notice, remember, the total area has to stay 1. The mean is still 0, which is the mean, median, the mode. So it's mounted up, centered at 0. And so we get this to work out like this. We see the symmetry here, but we see the smaller S is, the more of the area is near the mean, and the taller it is there on the mean, but the larger S is more spread out. So this has the same meaning that we thought before about the standard deviation. Larger standard deviation is more spread out. Smaller standard deviation is more tightly packed in. Okay, here's a Geometry Sketchpad sketch that I put together that has some normal probability distributions graphed. This is the standard normal distribution. Mu is 0 and sigma is 1. So the mean is 0 here, centered up on the y-axis. If you go to the right one from that right here, you get the inflection point. Let me, let's see. Let's put that back in. And this is one here. Let's get this. It's another one. The blue one is another normal. And let's move it back to the standard normal, close to it. Okay, and let's see what happens as we change the mean. As we change the mean, you can see that it's just sliding the thing left and right. So it's a horizontal translation. So that's changing the center. Okay, let's center it back up at 0. Okay, what happens as we change the standard deviation? As the standard deviation, it gets, you want to think maybe wider. It's, in ways that doesn't make sense because it goes from negative infinity to infinity either way. But it's this important part here in the middle. It's a little shorter in the middle, a little taller on the outsides. But what's happening is it's basically fatter. So what's happening is it's more spread out. That's the main thing. It's more spread out when it has a larger standard deviation. Now the total area has got to be 1, okay, but it is more spread out. Now when you get a standard deviation less than 1, now we see it's starting to get really tightly packed in near the center, near the mean. And by necessity, that makes it taller in the middle, right? Our overall height is taller. So the tallest point is lower when you have a bigger standard deviation and higher when we have a smaller standard deviation. So that's changing variability. And so then we can have very different variability, and then we can have different center as well. The inflection point is always there at 1 standard deviation away. You can see that. So that's kind of nice. So that shows you how you can get see that as see it dynamically moving around. I think that's kind of helpful to see what's happening with changing the mean and the standard deviation. This one over here I have set up where I can actually just type in a particular mean and standard deviation if I want and get it to work out. Okay, so I think that gives you a pretty good idea of the basic characteristics of a normal probability distribution, at least what the PDF graph looks like. And so you can see what that's going to be. And in the next video, we're going to come back and see how we can do some area computations here, which are, of course, probability computations.